So let's investigate this circuit. Before we start, what I'd like you to do is just think about this. What we're going to do is investigate the current against time. So we're going to put current as a time dependent variable against time. Look at that circuit. Imagine initially the capacitor is discharged, and then I switch on that step voltage of 10 volts. Look at the circuit, and I'll just give you a minute to think about what will happen, sketch what will happen, and what will be the steady state, and can you work out any values? And pause while you do that, and then we'll look at it at the end and see whether you're right. So let's have a look at it. What we want to do is to end up with a function that describes the current in this circuit. So from Ohm's law, that will be the voltage V, sorry, because it's not AC, over the impedance, the total impedance of the circuit. ZT, the total. So that's the formula we're going to apply. Current is voltage over resistance. But what we're going to do, first of all, is convert this into S space. So what we're going to do, we're going to find IS in S space, which equals V in S space over Z in S space. And then when we've got that, we're going to find out what that transforms into as a time-dependent function, and that will be the function that we plot. So the first thing to do is to transfer to S space, and then at the end we'll get a function that hopefully looks like something in here, so that we can then transform back and see what we've got. So that's the plan. First step, what's the voltage? What's the transform for the voltage? Step voltage. Second, what's the transform for the total resistance of the circuit? So we've got a resistor and a capacitor in series, but they are in parallel with another 2 ohm resistor. So let's see what we end up with. Yeah. So we've got Vs is 10 over S, and I think this time I've managed to avoid 5, so we should be okay. Zs equals, so what have we got? We've got a 4 ohm resistor and a 6 farad capacitor. In parallel with a resistor. So product, so times 2 over sum. 4 plus 1 over 6s plus 2. So that's our transform in S space. Now it's just algebra. We multiply out this bracket, 2 times this, 2 times that. This bracket's not really necessary. We can add the 4 and the 2 together to make 6. So we can do some simplification straight off. Multiplying out the brackets top and bottom, we get 8 plus 1 over 3s effectively, over 6 plus 1 over 6s. There's no one way to do these things now, but the sorts of things that are going through your head are, I don't like this 6s here being underneath. I could do with multiplying by 6s to get that at the top in this fraction, but that would mean I'd have to multiply that by 6s, this by 6s, and this by 6s. So we could do something like that. Actually, that might help because I'd have 6s over 3s, and so that's going to simplify quite a lot if we do that. So that's probably a good idea. Take this 6s that's underneath in here and multiply through by 6s. So every term, top and bottom, multiply through by 6s. and see what you get. Hopefully get this. I think you'd agree that it looks better, doesn't it, than it did before. So that's a good little trick to have in your mind. If I've got a fraction underneath here, or a fraction on top, if I multiply through by that, I'll actually make it better. I could have multiplied by 3s, but that would have left me a half s on the top underneath here, so maybe 6 would have been better. Okay? So that's an expression for ZS. We've got an expression for VS, it's 10 over S. So now we can come up with an expression for IS. So IS equals the voltage, which is 10 over S, over this lot, which is 48S plus 2, over 36S plus 1. That is the voltage divided by the resistance. So now let's look at this. Look at the bottom. And the top. I've got one fraction, 10 over S, this one, divided by another fraction. Now if you think back to your work with fractions, if I'm dividing one fraction by another fraction, I invert the bottom fraction and multiply. So I can actually now write that IS equals 10 over S, the top fraction, multiplied by the inverse of the bottom fraction, which is 36S plus 1 over 48S plus 2. So we end up with this. Now let's look at this for a sec. We've got this on, if we look at the bottom here, we've got S times 48S plus 2, two fractions multiplied together. Let's look back at our table of transforms. If you look at our table of transforms, remember we're going to end up going back to something. We've got something over S, and we've got something over S plus A. So with that, if we think about it, we've got, well, not quite, but if we look at it, we've got something over S, which is this bit. And if I were to divide top and bottom by 48, I'd have S plus some number here, wouldn't I? So in other words, what I want to do now is to use partial fractions to separate out these two bottom terms. So what I'm going to do is use partial fractions to separate these terms. I'm going to write that 10 times 36S plus 1 over S times 48S plus 2 can be written as, is equivalent to, some number over S plus some other number over 48S plus 2. I separate it out, and I use the method of partial fractions to find out what those values of A and B are. So focus on the right hand side, recombine them, and use the algebraic method that we've learnt for partial fractions to find the values of A and B. And I'll just pause this while you do it, and then I'll put the solution up and we'll carry on. So using partial fractions, we end up with this. This is the bit we want to try and transform, this bit, into something over S plus something over 48S plus 2. So we cross multiply, or we make the denominators the same here. So A times 48S plus 2 plus BS. Equate numerators, and we end up with this. And so, taking that, we then let S equal 0. If we let S equal 0, this bit goes, and so we can find out what A is. A equals 5. But to find B, we want this to equal 0. So 48S plus 2 equals 0. Solving that little equation, S equals minus 1/24th. And plugging that into here, we can find B. One little trick is to multiply through by 24 to get rid of the 24 underneath. which gives us this. So B turns out to be 120. So we now know A and B. So the bottom line is we can now say our transform, our current, is this 5 over S plus 120 over 48S plus 2. Now we're almost there. If we look at our transforms, we've got something over S. We've got something over S. And what we want now is this one. We've got S plus some term, but S on its own. So the final step is to go to our final answer, which is this one, and focus on this fraction and get rid of that 48. How do I get rid of the 48? No, can't I look at it? It's already times by 48, so divide by 48. Yeah, divide every term, top and bottom, the 120, that and that by 48. And we'll end up with IS equals 5 over S plus 48 into 120 goes 5 in my book over S plus 1 over 24. And now we can go back to our table of transforms and transform that back. Yeah, 2 over 48 is 1 over 24. So, slight correction, this one should be 2.5 on the top over that. So now let's transform it back. Let's go back to our table of transforms and see what we get. 5 over S is the first one we want to transform back. 5 over S. So look at the transforms. 5 over S turns out just to be 5. So IT five plus the next one. If we look at the transform, what have we got? We're looking at this one, which transfers to this, look. So the number on top is the number in front of the exponential decay function, and the number here is the number inside the exponential decay function. So we can now go back to here and write down that this equals 2.5 e to the minus 1 over 24t. So that is our function that describes this. Ah, okay. Okay, I can see where I need to go. If I were to put that into autograph, it would now predict it, what it would look like. I hope so. Yeah. So we've got our prediction here. If we plot it on autograph, we get this. Starts off with a current of 7.5 amps and eventually drops down to 5 amps, which is this point here. But now we can predict how long. Look, it's around about 90 seconds for it to drop to a steady state of 5 amps. And if we look back at our original circuit and think about what it actually means, we can say, well, in the steady state, once the capacitor is charged, that circuit is no longer in part of the circuit, or that branch. So we just got this bit only. 10 volts divided by 2 ohms is 5 amps. But initially, with the capacitor discharged, that's as though it's not there. So we've got a 4 ohm resistor as well. 10 divided by 4 is 2.5. So altogether we've got 7.5 amps initially. And we can predict it, but the beauty of this mathematics that we've just done is that we can actually prove it. But more than that, we've now got a function that will tell us exactly what's going to happen when I switch that circuit on. What will be the current after 20 seconds? 6 amps. So a useful method. Okay? And all we've done to do it is algebra. Okay, I'll stop there.